Bismuth, in the atomic level, it's 6p or 5p orbital. 6p, maybe 6p, or 6 doesn't matter too much. Like 6s2, 6p3, it is 5 valence electron. Selenium has a little more, maybe it's 5p4. It has 6 electrons. When it forms the compound, from simple chemistry, we will know bismuth will be 3 plus. Selenium is 2 minus, because it needs 2 more electrons to close the shell. Then it transfers 3 electrons away, and in total, to satisfy this balance, then it will have 6 2. Like, right? This is closed shell. Then it has only 2 electrons there, only 2 occupied. Then all the p orbital are empty. Then in a simple way, all the bismuth s just occupied somewhere, low energy. All the bismuth p orbital are very high energy. Selenium. Then selenium, they are occupied. Okay, fine. Its S maybe even lower. Its P is here. Right? This is the first view. And then let's look at a little about crystal structure. Actually, if we only look at bismuth, and I see, let's go here. It's a little complicated. And look at bismuth, its neighbors. If you look around in a 3D, one bismuth atom, actually on the top I have 3 selenium neighbor, on the bottom another 3 selenium neighbor. And in this case, the crystal field tell you actually it's that's not that good way. Or selenium will be similar. How do we do it? It's easier to understand. Let's just look at selenium first. Just took one layer, because one layer just one triangular lattice. That's one layer there. Inside one layer, it just form many structure like this, right? And one guy has 6 neighbors, 6 another selenium, and in this way. Then that means if just look at the crystal field, it looks like the PZ orbital will feel less repulsion from the neighbors, right? Then the PZ orbital, is it true? Sorry, I'm afraid it's not true. Sorry. Let's see. I forget how to argue it. Let's just assume it's okay. This detail not very important, and it's XY and PZ. They are different, for sure, because in this plane, the Z direction and the XY in the XY they are different. They have an energy splitting, and for bismuth it's similar. You have another PZ XY, and then that we forget to put all the electrons there. We have electrons, and electrons we know all these states, because here we have to put 4 because there are XY, PX, and PY states. There are 2 orbital. There are 2 probably. This is slightly higher. Then near the frame energy, there's just the PZ orbitals. And they may be very close, but we don't know the detail now. Now we just assume all it is empty. All bismuth are empty, and this one are occupied. And then let's see, then observe the parity, whether their parity are opposite from here. If you put a PZ on bismuth, this is the inverted center, inverted selenium, this is bismuth, this is the PZ. What's the 2 possibility? Yeah. Then what's the parity here? This one, the parity this one make an inversion from here, from minus to positive, then sure this one is negative. In parity, this one, the inverse center is here. That's important here. You get inversion, minus to minus, and positive to positive. Yeah, and then it's positive. Different. Then which one is the bonding state between two beads? This is the bonding state because these two minus are close. In energy, this one should be lower, and then we know. Actually, PZ there will be two types of PZ. The energy lower one will be this one. It will have positive chirality. Whether it's true? Yeah, it's true. And then let's look at this one. And for selenium, we have 3 selenium actually. Here, here, here. But let's put PZ here. First at the center. As long as we put the center here, it's already decided that the parity must be negative, right? And then this one, you put a positive here. Then that means you should be this way. This one inverted to here. They make it consist. You have a negative one. And other possibility is if you put a positive one, you put opposite one here. Here is nothing. Otherwise, you violate the parity. And then this possibility actually, there should be another. And yeah, whether it's related or it doesn't matter. Then this tells us which one could have lower energy. Oh, there. There should be another one. There should be another possibility actually it's related with. Sorry. Positive. Positive minus. Sorry. And there could be more possibility. I don't know which one is more. Yeah, that's true. That's true. Okay. Because there are 3 orbitals, there's some possibility. Then we know it can form a bonding antibonding state. Then which one has the lowest energy could be? But for sure, this one actually here they have some bonding, even they are a little low. Actually, at least they don't have repulsion. But here, each 2 of them they have repulsion. For sure, this has highest energy. This one energy is okay, maybe a lowest. This one could be in the middle, right? And all some 2 are degenerate. But no question, this one is the highest, has negative parity. Then let's go to like. That means PZ there are many possibilities, but one PZ on the top will be negative. This PZ, isthmus PZ at the bottom is these 2, they have opposite parity. They tell you simply it's this picture here. The valence band and the conduction band, they have opposite parity. And then this opposite parity, like then when we turn on the spelled coupling, and the spelled coupling simply pulls this down to. Spelled coupling simply is this XY, this split. Larger, split even larger. Here, split even larger. Then this is pushed up, this is pushed down. And naturally, if the small coupling is strong enough, they just get inverted. And this is the case for these 3 materials. And unfortunately, for this one, the light one, small coupling is weak. And have some trend, but not enough to invert. And yeah, there's some possibility, like suppose we mix these 2 materials in some way. Just means we mix the spelled coupling. We can still tune it from a TI into a trivial insulator, but in between maybe there's some critical point. There's some band touching. You realize the 3-dimensional Dirac coin. And then let's see. Actually, the material has some problem here you already see it. This is the experiment result. In theory, result always assume frame energy is inside the bulk gap, and it's better put them cross the Dirac line. And this is just theory, but in reality, this chemical potential actually for those materials usually they cross the bulk bands, and that means when we talk about a topological insulator, we have interest about this in-gap states. However, frame energy does not stay inside the gap. And this is just material by material. For many materials, especially, for example, this one, there are a lot of defects. Then dope a lot of carrier just means the material is heavily doped. And then the chemical potential is in the conduction band, but the surface are still there. And as I said many times, as long as the inversion, band inversion is there, just then you will have surface states. And it doesn't matter where the frame energy stays. And then, well, but it's good from photo emission, you can measure it. Yeah, here fully the Dirac coil here is occupied, you can measure it. But in transport, suppose you measure the resistivity, the charge will flow from the bulk because here you have bulk states. The bulk has a lot of carriers. The bulk inside is metallic. And you want a topological insulator. However, in the end, the material prefers go to a it's a metal. Just the metal has topological states. And just because the frame energy not at the proper position. And then there are a lot of efforts to try to optimize the material. And some famous example is just mix tellurium and selenium here in the compound. And, well, for example, just mix some of them together and try to tune. This is just the material problem. And some of them has defects, some are not. Or one usually P-type, another N-type, then mix them. Luckily, in some position, they give you an insulating one. Until now, there are already some progress to, to really suppress the bulk carrier, tune the frame energy to the right position. Well, maybe we are still, but at some point, we're still waiting for the most perfect topological insulator. And why this material, they are famous, or people studied it so much. One reason, always most important reason, they are very easy to make compared to mercury telluride quantum well. And here, you just put this element together, as I heard. Sometimes, and put in the furnace, and well, in the ordinary condition, you can work, you can get the material. Well, that also means the material is very dirty. And there are a lot of, much more efforts to really improve it, increase the quality. And this is one reason it's easy to make. Second, the bulk energy gap actually is really large. From theory, you can read it even better. The bulk energy gap about 0.3 eV, and it's much higher than the room temperature. That means that's why actually many of these spectra just were observed, measured at room temperature. That means at room temperature it works. And you must remember the quantum Hall system mentioned. It needs really low temperature, like Kelvin, in 1 Kelvin or Kelvin order, or even lower, and extremely high magnetic field. Now we don't need it. We just have the right material, measure it even at the room temperature. You see the topological states. And so far, there are many materials. Actually, the material are mainly related in this corner, the elements of the periodic table. And the reason also quite simple, because these elements, they are heavy. They have stronger spin-orbital coupling. And I said this lambda is proportionally to Z4 or Z square. And for example, like this is bismuth, tellurium, selenium, and mercury, selenium, and there are also many other more. Even the crystal insulator tin and telluride, they belong in this corner. And actually, as I said, bismuth telluride was started as a very good thermoelectric material. And then actually here, many material here later they were discovered to be topological insulators. And then there's a natural question, are there some really connection between thermoelectric and topological insulator? And well, this is a kind of coincidence. And for topological insulator, we know that we prefer some heavy elements because stronger smell coupling, and also smaller gap. If the gap is too large, it cannot be inverted. We want to invert it. And then small gap and heavy. For thermoelectric, we know thermoelectric, this is the figure of merit to see it. This is the feedback, this is conductivity. Electric conductivity, this is thermal conductivity. And for thermoelectric, yeah, they prefer a large feedback and very conducting. This already means the gap might be smaller. And high feedback means you usually prefer some band, relative flat band than some heavy elements. And then that means very low thermal conductivity. Then many heavy atoms in the lattice will help this point. Then that means it also prefer heavy elements and a small gap system. Well, small gap sometimes also related with the application for thermoelectric near the room temperature. And then this means like if we know some very good thermoelectric material, then we can always first think whether this can be a topological insulator or not. And but you don't have to think at this point too much because they are already started on much. All these materials are calculated in the band structure whether they are topological insulator or not. And well, I think this is there are more material come out, and one is Heusler material. It has very similar structure with mercury telluride, but I think tomorrow in the talk of Claudia will give a talk about the details about this material, and I will skip these points. How much time I have? 30 minutes. Okay. Okay. Here I just show you another example about a weak TI. So far we mentioned 2D TI, mercury telluride quantum well. It has edge states and it's proved by measure the edge conductance, the quantize the edge conductance. 3D TI is confirmed by measure the surface states. Just to see clear Dirac coin in the gap, even at room temperature. Then where is the weak TI? The layered 3D material. And then now we have idea. Let's see. This one, let's see, start maybe to detail. Let's just go to one material. This material actually looks a little complicated, but let's forget this potassium material. What this material exactly is. Now we know the formula of mercury telluride. And now just play very little chemistry. I write a formula in this way because selenium has 6 electrons, valence electron atom, and mercury and antimony, this is 1. This antimony has 5 valence electron. And I get a new formula, just this formula to keep the charge balance. And different is this material crystallizes in a different lattice, not this cubic anymore. And get this mercury and antimony form a honeycomb lattice. And in between these honeycomb layers is this potassium atom. Well, potassium then just stay there to balance the charge, stabilize the lattice. In the band structure, their states are far from the Fermi energy. We can forget it. And important is, we know in mercury telluride we have the band inversion. Actually here, the mercury antimony, it also has band inversion. Just here, mercury telluride, we have an inversion in this way. This is the S state. Here, we still keep the inversion in this way. Out here, we don't have cubic symmetry anymore, luckily. We just have a gap. Just this is the band structure. We have a gap. We just break the cubic symmetry in a different material, not by strength, just design a different material. And here, every mercury antimony honeycomb layer give you a band structure like this. It has inversion. Then it's a 2D TI, right? But this is a 3D material. Then naturally, these 3D materials stack together and form a weak TI. And then this is not very different. And then this is its dispersion. Actually, how the dispersion looks like. This is the bulk band structure. At the gamma point, it has inversion. You see S is below P, or the P here, you already have a large gap. And at the Z point, also S is below P. And, but here, along gamma and Z, dispersion is really weak, relatively flat. And this introduced, like, because here you have an inversion, you project out to the gamma bar. Here you have a Dirac point. Actually, it means it's here, this Dirac point. Z point, you have another inversion, you just project out. You have another Dirac point at Z point. That means in the surface Brillouin zone, this means the side surface. You stack them along Z direction, but the surface state is here. And here you have two Dirac points at gamma and Z point. And for quite a while, people believe these states cannot be stable because of the scattering between them. Later, people just more and more detail realize if we don't double the unit cell, like their material, if the unit cell is doubled and like have some charge density with charge density instability like that, you have some reconstruction in the material. And then, well, these two will cancel each other. But without this possibility, it's still robust. And then this material actually here, let's go to the crystal structure. This is the primitive lattice. And here we have a honeycomb layer. Every layer is quantum spin Hall. It's 2D TI. And then there's another possibility. Indeed, in nature, there's another possibility. Oh, sorry, I don't have it. We have a honeycomb layer here. And this is mercury. This is antimony. And yeah, maybe I write it this way. This is one layer. If we just stack them to 3D, just repeat, it becomes a weak TI. There's another case. In reality, actually, the material crystallizing this way. The unit cell indeed get doubled. Doubled in a way. If here is the inverted center, actually the potassium, you have a mercury here. You have mercury here. That these three positions are this antimony. It exactly means it's doubled. Then after the doubling, originally at gamma and Z, you have two Dirac points, right? Now, after doubling, your Brillouin zone becomes half. This one is folded to here. And once I believed, when they fold together, it's not stable, they will open a gap. I even don't think it further. Actually, later, Andrew studied this material and realized there's additional crystal symmetry in this material. Actually, even they folded together, this can protect them robustness. This is a kind of crystal insulator. And like it's protected by crystal symmetry, but not by Z2. And, okay, I skipped this one. Maybe we can quickly. Yeah. In the very end, I will say a little about this topological mirror insulator. And just again, we look at the band structure. There are some detail. And here, this is the crystal structure of the tin telluride. It's just a rock salt. And tin and telluride, each of them form a FCC lattice, two FCC. Just we put them together. Then this is the FCC Brillouin zone. In the band structure, actually, there's a band inversion at all the L points, these red points. And there, in the Brillouin zone, there are in total 6 non-equivalent L points. And these should be the points to count the parity. Actually, every L point has an inversion. However, because there are 6 points, whether they're in inversion or not, the Z2 is trivial. And we don't think it's topological. And actually, first, it was discovered, indeed, there are some surface states come out. These surface states stay like there's a Dirac crossing. But this Dirac crossing not stay at the X point or gamma point. And although the projection like here, you get X. And is a little away, and about it's robust. And later, people recognize the reason. The crystal structure actually has a lot of mirror planes. Either of them, you put the XY plane, YZ plane, and this plane. For example, here, this one connecting the L1, L2, this plane. And this plane will protect the, the crossing, protect the edge states even when they overlap together. And how, I would see. Then how this happen? For mirror symmetry, there's nothing more. Like we know if a system Hamiltonian has a symmetry, then the consequence is there should be a degeneracy in the band structure, right? And a time reversal guarantee the degeneracy here. If you have a mirror plane, like for example this plane, when this plane projected to the surface, it will be a line. Along this line, there will be some degeneracy guaranteed. And let's look at this structure. Like we have, it's a little complicated. 2 points, 2 inversion, projected to somewhere. All these points, they stay in the mirror plane. Then the consequence is this point, there will be 2 Dirac coils, right? Maybe their energy are totally same, they overlap, or maybe they can different. But this is the mirror line. This line is the projection of the mirror line. And this mirror plane guarantee, like, if you have a mirror plane, this guarantee the spin will be, mirror symmetry spin always perpendicular to the mirror, and in this plane. And then then that means in this plane, spin up and down is a good quantum number, only in this plane, right? Now we come back to the old story. Then if it's a good quantum number, spin up, you can define a chain number 1, maybe, and spin down, give you opposite chain number. And then you will get a kind of mirror chain number 2. Yeah, you will get 1. But this is only well defined in this plane. Go away this plane, you lose the symmetry. Up and down are not a good quantum number anymore. Then this number guarantee when it projected to this plane, you should have a pair of crossing. Like you will have a spin up crossing here, and then you have a spin down opposite. And it will happen along this line, but not necessarily but it does not tell you which point, X or gamma or somewhere, or random point. But it should happen there. And simply because you have some this edge state here, they may be hybridized, open the gap somewhere else. And about along this line, this crossing is robust. It's guaranteed either by this mirror symmetry. And then I just want to make it clear is like we have inversion, then we will have surface states. And then whether this surface is robust just depends whether there is a kind of symmetry to protect it. And for the topological insulator, it's time reversal symmetry. If you go a little more, like if it's not a topological insulator, the Z2 is trivial, there are 2 inversions, maybe there's some additional crystal symmetry protected. And this will really depend system by system. And here is a case, a mirror symmetry protected. And as I said, this double layer structure, double layer with TI there, here there's some protection from the non-symmetric, like from a kind of glide plane, mirror plus a kind of shift. And well, so far you don't have to care too much detail about this figure. But here, this may be the very last slide here. Here the one very important picture is we keep see is this band inversion. And well, how to really quantitatively decide the band inversion, you have to calculate the Z2 always. And about this band inversion, like suppose when the coupling open a full gap, and then it's usually you get a topological insulator because now you get an insulator. And then on the surface, you have metallic surface states. But at some case, the system actually this band touching, this is really a 3-dimensional band structure. The band touching, if you don't include spinel coupling, there are many possibilities, many areas. Like usually they form a nodal ring or some sphere, they have a touching. And when you turn on the nodal coupling, sometimes there are some isolated points, this band is still touching. Even a new line they're touching, these touching points, that can be possible. There's no guarantee, say, you always get a full gap. And then what's happened at this point? And actually this point, if you look locally, it's a three-dimensional Dirac point. And actually this is exactly a case of three-dimensional Dirac semi-metal, as you will learn in the afternoon. And here, well, if we assume inversion symmetry, and the time reversal, all the bands are double degenerate. And this crossing point, like actually every band have spin alpha and beta. And if you break the inversion, the spin degeneracy will split. And then, but this crossing point, they can usually survive. Then you will get a crossing point without spin degeneracy. Then this crossing point simply called a wire point. They are just like each wire point split, like one Dirac point split into a pair of wire points. And these wire points have chirality, you will learn later. And about the consequence is also this kind of special semi-metal, because of the band inversion, it will also give you the surface states, topological surface states. It's very robust, just guaranteed by the inversion. Then here simply tell you this band inversion picture can explain you a lot. Like as long as you figure out the inversion, then later think about other symmetry or other possibility. And then you can easily address where the surface state is, whether it is robust, and in which case you can kill it or you can protect it. And then that's all. I hope now you can have a roughly feeling about what is a TI and have a taste about these materials, and exactly for this typical bismuth ceramic and mercury materials, and you can get a taste exactly like what happens in the material and what really drives this topological band inversion. And good, now it's time for questions. Thank you.
I didn't fully understand the origin of this critical length to have band inversion in these wells.
You mean mercury?
Yes.
Okay, critical length. I will see. Oh, this just seen this way. Always, you just start from a even simple band structure. So, this original mercury, we only plot this. This is S, this is P, right? And well, actually, most case, this is still S. P is here, only partially inversion. Let's suppose we have a band structure, S totally go up, P totally go down. Actually, that means at every K point, you have an inversion. Then 4 times, 8 times trivial, right? When we mention the inversion, it's only invert locally. This means like actually this state still feel it's an electron state. And this state still feel it's a Hall state. They have opposite sign of effective mass. And for normal insulator, like suppose you have a gap in this way. It's bulk. You make it thinner and thinner, and that means its band gap just increase. Right? This is the bottom. This, like suppose this is the thickness. Very thick is the bulk limit, and this side is 0. Very thin is the 2D limit. You make it 2D and 2D, more 2D, then the gap will be larger and larger. Right? Here, nothing more. You just keep the electron band should go up. This band should go down. Just like put them in different position, shift in energy a little. You get it. And then that means in the limit, the red band finally will go out, go top. The black one will be here. If you plot a band structure, okay, you have a band structure here, in this way, right? It's a normal insulator. But here, you still have some possibility here. Most important, this one also split. Important, first, now you have a gap between the red and the black. You have a small gap. It has inversion, these two. Yeah, now this quantum well won't benefit from the inversion of the bulk, but generate one additional gap.
So you're drawing on a picture as a function of the thickness of the sun?
Yeah. You like a very thick one, you can make it thinner and thinner. Yeah.
Yeah, so I think I kind of understood why appears a surface state, for example, in bismuth-selenide, but I didn't get why this helical spin texture.
Helical spin texture. Okay, very good question. In 2D case, can you understand why it's up and down? Yeah, actually, you understand the helicity of Rashba?
Yeah, this is.
Then it is same with Rashba.
It's just the same.
Just
There's
same.
no other topology reasons. It's just the potential is asymmetric to one.
Yeah. That's like all in this way. All the physics you observe locally is everything about spelled coupling. Give you the S dot L, some alpha. As long as the sign of the alpha is fixed, then they log in this way or this way. Just depends on the sign of alpha. But locally, they have the texture.
Okay.
Yeah.
So then the topology gives you the surface state.
Yeah.
And then spin orbit gives you the spin texture.
Yes. And spelled coupling also sometimes involved in the band inversion. Yeah. In bismuth telluride directly, it's spelled coupling post-band cross. Well, mercury-telluride, they're slightly different, but it's another relativistic effect.
Okay, so that's a double. So it makes it the band inversion and it inversion.
Yeah.
When you talk about weak three-dimensional topological splits, you mentioned that they can be realized in layer units.
Yeah.
So I was wondering, is it like necessary that you are they only realized in layer units, or they can be like layer and layer?
Oh, good question. Like layer, just a good way to tell the story, right? But in reality, if the interlayer bonding is very strong, it's already look like a 3D. Yeah, in chemistry, obviously. Yeah, but maybe there's a possibility like, suppose if we count the parity, we can easily plot many possibilities, like in a 3D Brillouin zone, a cubic way. We have a gamma point. Suppose we have a minus here. All other points are positive. Here we have another minus. Total Z2 is trivial. But later, the other index will become like 1, 1, 1. 1, 1 simply tell you have some equivalent of stacking along 1, 1 direction. But maybe your material is a very 3D material. Yeah. And, actually, yeah, I see a little more like how this one is calculated. And well, in formula, it looks very complicated, but actually, this one, they are very simple. Where is this one from? This one corresponding, you just take it X, Y, Z. This one is from this plane, this 2D plane, not including gamma point. This plane is the YZ plane here, right? You have 4 time-reversal invariant points. Make a product, either positive or minus. And then you get 1 or 0. Then here, the Y, you take another plane, the XZ plane, and for this one, you take this plane. These 4 points, make a product, then you get it. And this is just a way to count it. And this is just a mathematics about that. But sometimes in the formula it's very confusing. But just take 4 out, not include the gamma point, away the plane. and count the parity, you will get all these 3 parameters one by one. No. Another question? Yeah. Which one? Crystal. Yeah, this is a typical crystal insulator. Yeah. I just call it differently, but same. That's it. Yeah. Yeah. Thank you.